Hello, everybody, and a really warm welcome to my talk about industrial AI and how to apply industrial AI in our shop floors, in our industrial applications to gain really benefits for the production staff, for the guys who are working in maintenance, who are service technicians, who want to drive the world with AI and want to use it as maybe you do in your everyday life currently. So, intelligent data analysis, of course, has various fields. Today we are using AI maybe by using the Microsoft Copilot, by using ChatGPT, and the key idea here is that we want to use it as efficient and simple as possible in our daily lives. We don't want to change our work steps, our different behaviors, but we want to integrate the usage of AI to be more flexible, to have our calendars up to date. So for recurring processes that we don't want to do manually, but we want to have a guidance, and that is also the spirit for industrial AI applications. With our software solution MLnext, we want to ensure that people who work in maintenance, who work in various fields and industrial applications can use MLnext seamlessly to create machine learning models and later deploy them on the shop floor. So we talk to lots of different stakeholders throughout digitalization in various domains. We talk to guys that need or that are responsible for collecting the data on the shop floor. We talk with guys that are driving the maintenance teams at system operators or maybe machine builders, service technicians. And if they think about digitalization, we often hear that they see the benefit of digitalization and industrial AI applications, but they don't really know how to implement these applications in order to have real benefits to drive their market, to drive their applications. And that is something that we see that in many domains, our so-called domain experts, so the guys that are really brilliant in operating the machines, that know about, for example, injection molding, that know about soldering, that know about solar farms, and so on, that they think of digitalization more of an increased workload currently. Because let's be honest, who are the guys who are maintaining the digitalization setup? It are mainly the guys that are also responsible for operating the machines. So for them, it is often only an additional workload compared to what they have to do now, and they really need to enable their daily life and their work by applying industrial AI. So often we hear sentences like, yeah, we start with data collection because someone told us that Industry 4.0 will be changing the environment and we need to collect data, visualize them and analyze them, but they don't have the concrete applications or the precise applications in order to implement all of these features. And that brings us to our key message and what we say our customers when we think about data analysis and think about data-driven benefits in general. You can't manage what you don't measure. You really need to start measuring the data at the machines and bring together data from the different operating states of our machines with our overall maintenance system, with the MES system and SAP system. So let's think about our daily lives. If we want to improve our energy efficiency, for example, in our households, it is quite okay to get a feeling of how much energy is consumed in my house. Yeah, I can go downstairs and look at the energy meter to find out or how much data is consumed. That's the easy part, bringing transparency. But if we want to optimize something, then we really have to take a look and go deeper into the applications to maybe find out if we could switch the temperature of our fridge to save energy, or maybe to shut down the Wi-Fi router at night. And maybe the Wi-Fi router at night is responsible for all of the updates. So later, I saved some energy, but I don't have the newest updates anymore because the Wi-Fi router tried to implement or try to do the updates every night. So that is our philosophy, to say if we want to manage something based on data, we need to measure the correct points. And I will talk about how this can be implemented. And I will talk about and want to talk about the new chances of digitalization. So how to optimize our production with this digitalization techniques and how to implement the industrial AI at the end. Because for machine learning, data is the basis. Yeah, data is the gold of digitalization. It's the most valuable thing in digitalization because with the data, we can create dashboards to support our maintenance teams. And we can apply machine learning models in order to have condition-based maintenance, for example, to predict unusual behavior at machines and counteract or interact even before a critical failure happens. So when we want to implement machine learning solutions at our customers, it are mainly these 4 steps that are needed in order to come to our AI application. Yeah? First of all, we have to measure the data. We have to use energy meters, analog inputs, maybe we have to duplicate the signals, and also many of our PLC systems already have an open interface, an open data interface to collect the data on the shop floor. For that, data collection and storage is crucial to have the correct and precise data quality. And I'm a data scientist, so I worked at Phoenix as a data scientist for some years and also did some research in data science. And in first place, let's be honest, if I start in the industrial AI applications, I think I have AI in my pocket, I can conquer the world with that, and we will help everybody. But in the end, that's only one part of the medal. The other part is that we need the domain experts. We need the guys that know the processes, that are really aware of the processes, and that we help them implement AI by collecting the data in a probable manner. Yeah? And sometimes I'm asked, why is Phoenix Contact, as an automation company, also investing in AI? Isn't AI made by Microsoft, by Google and co? Of course, they have their domain expertise in big data and data analysis, but when it comes to the shop floor and when it comes to OT intelligence or implementing AI on the OT layer, then we analyze the data that the SPS or the PLC is operating anyway. Yeah, so for Phoenix Contact, it was just a logical step to do the analyzing or the analysis of the data that we are processing with the PLC anyway. And that's why we know that for OT, it's not about time synchronization on second level, it is about time synchronization on milliseconds level. Because if I have a machine and I want to use vibration sensors, an energy meter and temperature sensors, I need to synchronize the data points in order to form a time series. Yeah? And it's the same in our daily life. If I want to improve something, I really need to know every step in my optimization in the frequency that I need to visualize this, that I need to analyze it further. So that is really a key for us to come to analysis. And once the data collection is done, for a domain expert, a first good step is to implement a dashboard. Yeah? So what I see is, when I talk to these domain experts and I just show them the data of their machine in a plot, in a graph like this, then they say, oh, that's interesting. Or they say, oh, that's unusual. And that is exactly the behavior that we want to later have in our AI. We want to have the AI as an experienced maintenance guy that comes into the offices, that comes into the production lines and say, something is unusual. Yeah, that's an unusual vibration. That's untypical. Or maybe I hear a noise. I hear something that is not quite typical for my normal behavior of the machine. And this information, that is already encoded in the data. So small peaks in the vibration or a little bit unusually high energy consumption because the friction of my drive shaft is a little bit tougher than usual. And that are exactly the first signs that we want to analyze with our AI. So our goal with MLnext is to train a machine learning model exactly on that behavior, to simulate the process. So we're collecting data of a production process for 2 or 3 weeks, and then we learn an AI, a machine learning model, to simulate the behavior of the machine in a similar way that the domain expert, the experienced guy, would simulate, they have a kind of simulation of the machine in their head of the ideal operating. So if I come to an injection molding machine, then I say, okay, I know that it should sound like this, it should smell like this, it should behave like this, and this ideal performance is encoded in our machine learning model. And then later we can deploy this machine learning model on the shop floor in a most scalable way. So our machine learning solution can be directly executed on a small PLC system. So because it's obvious, the system that is processing the data anyway should also have the analysis. Yeah, and for many applications, like automated quality control, for example, we really need fast response times. Yeah? So the machine learning model, the inference of the machine learning model, so implementing it, the data running through the machine learning model, cannot take longer than, for example, 500 milliseconds, because that is the normal frequency of my machine. If a machine produces a good every 500 milliseconds, or a production step is realized in 600 milliseconds, then the result of the AI cannot take 1.5 seconds, because I will be the limiting factor. And that is why we investigate if it's ideal to implement the machine learning model directly at the PLC or at the edge PC, or later also on the industrial PC, or maybe also in the enterprise level at the customer, so in the IT or in the cloud, based on what is needed. So if we have anomaly detection, yeah, we need a maintenance guy to do the work anyway. So maybe for an anomaly detection system, it's okay that it runs in the cloud and have a response time of 5 to 10 seconds, because nobody can interact with it faster anyway. So that is what we really have to investigate based on the applications that we currently implement. So now I want to talk about different applications that we have on the shop floor. And the first one, and this is also the first one that we at Phoenix Contact investigated, is anomaly detection. So anomaly detection is this experienced machine operator and to encode the knowledge of the machine operator in the machine learning model. So we're collecting the most crucial process parameters. Now let's imagine an electric motor. What would be good for an electric motor to monitor? Vibration, electrical energy, maybe temperature. These are the values that we process and store, and then create the simulation of this electric motor with our machine learning model to do anomaly detection. Yeah, and that is something that we really can benefit from if nobody needs to label the data. So for anomaly detection, labeling the data is really expensive, because we need an expert to do it. We need to have an expert who sits down and writes down if this motor is behaving correctly, if the next motor is behaving correctly. So anomaly detection from Phoenix Contact can work without labeling process because of the simulation idea. Next, what we call virtual sensor or smart sensor. To be honest, we are not quite clear on how to name it, but what the key idea is, that we want to have a measurement system, like measuring the process parameters, and then we want to later replace this real measurement device with the machine learning model. So let's imagine that we have a machine, or we have 10 different machines, and we want to monitor the process parameters more precisely. So for example, product size, product weight, and so on, for our quality control. And for the quality control, we need to implement this at our 10 machines. We take one machine and collect the data with a measurement system, and later we learn the machine learning model on the data of this measurement system. And for all of the remaining 9 machines, we only implement the machine learning model we trained on the first machine and deploy it. Yeah, and that will later save us money for all of the measurement systems. So in a normal setup, we need to install 10 times the measurement system, and now only 1 time or 2 times, and the rest is done virtually by the machine learning model. And that's why we call this virtual or smart sensor application. Next thing, and I think that is even a better use case for quality control, it's classification. So based on the data, I want to classify in the end if my product is faulty or not, for example. So end-of-line testing could be a typical application for classification. So in the end, I collect all of my different time series data, so the temperature where the product was produced, the most crucial process parameters again, like pressures, like maybe throughput, cycle times, and so on. And based on analyzing the cycle time, I can later classify if my product is good or not. And maybe only the products that my machine learning model will classify as faulty, or where the process parameters weren't perfectly set, these products will later manually be checked. And for all of the remaining products, where I know all process parameters were perfectly fine, I can directly forward them and automate the process of quality control. Last but not least, when it comes to applications, I want to talk about forecasting, because of collecting the data gives us also potential to predict the behavior of, for example, the machine. A typical application would be energy forecasting. So I think everybody of you maybe know that for energy forecasting in solar industry, it is quite good to do an estimation based on the weather data. And if you have a good estimation on the weather data and a good weather forecast, you will very likely know how much your photovoltaic system is producing throughout the day. It is a little bit more difficult and complex when it comes to energy demand. So if I have a production line with all of my different machines, maybe also my shift schedules could be a good starting point to know how much energy is used. But with our machine learning solution, we can learn on the energy demand data. So if we collect the energy demands, so for example, for energy saving or for resource efficiency regulations, we also need to collect the energy data of our most significant energy users. Then we can use this data to not only do the reporting in the end, but also to forecast how much energy is used for certain days. And this is maybe very important for sector coupling. Yeah, so maybe I have my production, I have my EV charging park, and I also have my photovoltaic, and I want to know when to use my electrical battery storage, when to charge my EV charging, and when I need all of my energy for production only. Because let's be honest, we need to ensure that production can run 24/7. So with the energy forecasting in MLnext, we can decide on in which spaces, in which time points it is most beneficial to, for example, load our battery or to load the car, to have a good energy demand analysis. So I hope that I give you some small hints and some example applications on what MLnext can really do and how we can implement AI. And yeah, I would say for the digital guys and also for everyone sitting here, I would invite you to come to our booth to see what MLnext can do, because in the end, directly behind this wall, we have someone that can showcase MLnext and show you what MLnext looks like in action and how to really do it step by step. From the data collection to the data analysis, training the machine learning model and deploying this machine learning model. And of course, we also can show this in a customer demonstration. So for all of the guys digitally available that say, okay, I'm not here at SPS Fair, we can also show it and demonstrate it to you in the customer speech. So thank you very much for your attention digitally and also here. And I wish you a nice day. Thank you so much for your attention.